Let's watch some crazy stuff, yo!
Gary! I was just looking for the sports channel, Gary.
Welcome to geometry class. In this video, we're going to look at 18.4, the end of chapter 18, and we'll finish up with the surface area of spheres. Okay, our warm-up is about what we did yesterday, though. A cylindrical can of pears has a label that covers the lateral surface area, so that does not cover the top and the bottom of our can. If the height of the can is 18 centimeters and the radius is 4 centimeters, how much paper is used to make the label? So our surface area, the lateral surface area, is just going to be 2 pi r, the circumference of the circle, and then we're going to multiply that by 18. So we have 2 times pi times the radius 4 times the height of the can 18. We multiply all those together. We are going to round to the nearest square centimeter, and we're going to round that to 452 centimeters squared. Okay. Oops, that's just what we're doing for the week. Here, we are going to investigate the formula for surface area of a sphere. The surface area of a sphere with radius r is given by surface area is 4 pi times the radius squared. Now, I believe this picture goes to something we're going to be looking at on the next slide. So I'm just going to make this bigger so I can flip back and forth to it. And in example 1, it says a cylinder and a sphere have the same radius r. The sphere fits inside the cylinder, so the sphere intersects each base of the cylinder at one point. So here's the top of our Pringles can, and our sphere touches at this one black dot point. Same thing at the bottom. Here's the bottom of our cylinder, and the sphere touches it at one point. Write the lateral area of the cylinder in terms of radius r and height h. This is kind of what we did in the warm-up. Our lateral area is going to equal 2 times pi times r. That's our circumference. And we're going to multiply that by the height h. B, what is the height of the cylinder in terms of radius? Well, if I go back here, if I go from the center of the sphere to the top, that's one radius. And if I go from the center of the sphere down to the bottom, that's another radius. So overall, that height would be 2 times r. So what is the height, h, in terms of radius? The height is 2 radii. So now part C, we're going to combine A and B. What is the lateral area of a cylinder in terms of r only? So I'm going to take this equation here, 2 pi r times h, 2 pi r times h, but we're not going to put h in there. We're going to replace h with 2 more r's, so times 2r. And we can clean this up a little bit. This 2 times this 2 is a 4. We have a pi, so I'll put my pi here. And then we have r times r. That's r squared. Well, look at that. The lateral area of a cylinder is 4 pi r squared. And the surface area of a sphere is also 4 pi r squared. Now in part D, let's read it here. A hemisphere of radius r fits inside a cylinder with radius r and height r. One base of the cylinder is the circular surface of the hemisphere. So the top of the cylinder is also like the cross-section of our sphere. And the hemisphere intersects the other base at one point. So here's that one point where the bottom of this sphere intersects with the bottom of the cylinder. Is the surface area of the hemisphere half the surface area of the cylinder? Well, when we cut the cylinder in half and the sphere was inside, we have this extra bit here. Let me color over it in red ink. So now this red region would also be part of the surface area of the sphere inside. So the short answer here is the surface area of the hemisphere half the surface area of the cylinder? No. And I guess for the explanation, we'd say to close off the hemisphere, we would need a circle in addition to half of that surface area. So again, here we have kind of a bowl shape. When we cut the sphere in half, we would need a lid for that bowl. So this red that I'm scribbling over would sort of be the red lid for that bowl. So is the surface area going to be exactly half when we cut it in half? No, we would have to add in that additional circle. All right, what's next? A hemisphere is half a sphere. The surface area of a hemisphere is half the surface area of the related sphere plus the area of its circular base. So again, if I have a sphere, the surface area of that is 4 pi r squared. If I chop that in half, we now have kind of this bowl shape. So we would have half of the 4 pi r squared. That would cover sort of this blue part of the bowl. But now the surface, or the top of this, we would need a lid for this bowl. So what I'm scribbling over in black ink there, we would need another circle of pi r squared. So that'll be, So in example 2, they want us to find some of these surface areas. So let's break out our new formula. Surface area is 4 pi r squared. This 8 is the diameter, so we're going to cut that in half. 4 times pi times 4 squared. 4 squared is 16. 16 times 4 is 64. So we have 64 pi. Our units would be squared feet. The directions do tell us to leave it in terms of pi. All right, now the next one, our surface area, is going to be 1/2 of a sphere, 4 pi r squared. And then we are going to add a lid to the bowl, a pi r squared. So here they give us the radius. They just hand it to us. It's 3. So this is going to be, well, let's even do this. Half of 4 is 2. And then we'll have our pi r squared. And I guess we can replace that r with a 3, 3 squared, plus pi 3 squared. 3 squared is 9. 9 times 2 is 18. So this is an 18 pi plus 3 squared is 9 times pi is 9 pi. And that's going to add up to a total of 27 pi. And our units would be centimeters squared. Example 3. We've got gold beads like shown in the picture. They're used to make earrings. Each bead is a stainless steel sphere with a 24-karat gold coat. The density of the gold in the coating is 0.009 milligrams of gold per square millimeter. How much gold is in the coating of one bead? So our formula, surface area, is 4 pi r squared. So 4 is just 4, pi is just pi. Our radius is over here in the picture. Each bead, the radius is 6 millimeters. So this will be 6 squared. So let's see, 6 squared is 36. 36 times 4 is 144. So we have 144 pi. Our units there would be millimeters squared. And that is for one bead. Now, if I reread this part of the problem, the density of the gold is 0.009 milligrams of gold per square millimeter. Well, we have this many square millimeters, so we're going to multiply that number by the 0.009. And that would be approximately 4.0715. And that would be, we could round that off to approximately 4.1. Our units up here were milligrams. What would that be? mg, milligram of gold. So each little gold bead has 4.1 milligrams of gold covering the outside of it. All right, and I think this is our last example. Surface area of a silo to the nearest square foot. I'm going to draw some more pictures down here below. So here's our Pringles can, our cylinder, and that has a height of 60. In the picture, we can see the diameter is 20. So the radius will equal 10. And then sitting on top of that Pringles can is our hemisphere for the top of the silo. Again, that will be the same radius, r, is equal to 10. When we are determining the surface area, the bottom of our hemisphere, this red circle that I'm coloring in right now, is going to land on top of our cylinder, the blue circle. So we don't need to count the top and the bottom of our cylinder, and we don't need to count the bottom of our hemisphere. So our basic surface area is going to be the lateral surface area of the Pringles can, the cylinder. That is 2 pi r times the height. And then we're going to add to that the 1/2 of our surface area of a sphere, 4 pi r squared. Okay, and we can see here in the picture, the height of our cylinder is 60 feet. We've already established radius is 10. So let's plug those values in. Our surface area is 2 times pi times radius 10 times height 60 plus, let's do this half of 4. That turns into a 2 pi. Radius again is 10, so that will be 10 squared. So let's see here. 10 times 60 is 600. 2 times 600 is 1,200. And we got a pi there. Plus 100 is 10 squared. 100 times 2 is 200. 200 pi. So these add up to 1,400 pi. And that would be square feet squared. It does say round to the nearest square foot, so let's use the pi key on our calculator. 1,400 times pi, and we'll round that off to 4,398 feet squared. There's the surface area of our silo. If we knew we wanted to paint it and we knew each can of paint covered so many square feet, we could figure out how many pans of paint to buy. All right, now it's some practice time. Perfect time to pause the video, try the problems out, and then compare your answers with mine when you start the video back up. And in number 1, A and B, they do ask us to leave our answer in terms of pi. So in the first one, 24 is the diameter. Our radius will be 12. So we're going to do here 1/2 of our sphere, and that's 4 pi r squared. That'll be the dome shape. And then we need to add, the floor to that dome, or the bottom to this, would be another circle, pi r squared. So again, half of this 4, that's going to be 2 times pi. Our radius is 12, so that's going to be a 12 squared. Plus pi, r again is 12, so that's another 12 squared. Back to the first term, 12 squared is 144, and if we double that, we get 288 pi. Plus 12 squared again is 144 pi. And if we add those together, we get 432 pi. Our units would be yards squared, square yards. All right, and in part B here, a little easier. It's just a regular old sphere. They hand us the radius on a silver platter. So our surface area is 4 pi radius squared. That'll be 4 pi times 9 squared. 9 squared is 81. 4 times 81 is 324 pi. Units are inches squared. All right, in the second practice problem, the figure shows how a long piece of rope was wrapped around a cylinder to completely cover its lateral surface. So in the picture, I'm using red. The rope was all the way around the cylinder. It did not cover the top of the cylinder or the bottom. The rope is then taken from the cylinder and wrapped around a sphere. Will the rope completely cover the surface of the sphere? Why or why not? We could actually solve this without using math, just with a little deductive reasoning from those first couple of slides. But let's do the pure math way to do it. They're asking us, is the surface area of the cylinder greater than the surface area of the sphere? If it is, we would have plenty of rope to cover the surface area and have maybe some extra left over. If the surface area of the sphere is greater than the cylinder, all the rope around the cylinder is not enough to cover the sphere. So let's look at our surface area formulas. Here we only need the lateral surface area, and that's going to be circumference 2 pi r times the height of our cylinder. And then our sphere is just 4 pi r squared. The radius is going to be the same. This is 7, so our radius is 3.5. Same for the sphere. So here we've got 2 times pi times 3.5 times the height of 14. And we're going to say, is that greater than or less than 4 times pi times 3.5 squared. And I'm going to leave my answer in terms of pi. 2 times 3.5 is 7, and then times 14 is 98 pi, and that would be inches squared. And over here, 3.5 squared times 4 is 49 pi inches squared. So if we're taking rope off the cylinder, we've got that much area covered, and as we wrap it around the sphere, we have more than enough. It looks like we might even be able to do it twice, wrap 2 spheres with the rope we had stretched around the cylinder. Another way to do it without math, we could say the lateral surface area of a cylinder with the same diameter and height of a sphere is equal to the surface area of the sphere. The cylinder in this problem has a larger height, so it will cover the sphere and have plenty of rope left over. All right, number 3 might be a little tricky. If we look at it in its basic parts, we have a rectangular prism. We can find the surface area of that prism. We have a sphere on top. We can find the surface area of that sphere. But when we put the sphere on the prism, this little bit of area, this circle, is going to be covered up. So we're going to have to deduct that at the end. So let's see here. We've got 6 rectangular faces, and they come in pairs. So we're going to do 2. Let's do the front and the back. The front and the back here are 9 by 2s. 9 by 2. So that's front and back. And then we're going to have 2 left side, right side. So over here, this would be 2 by 4. So we have a 2 by a 4. And then we need the top and the bottom. The bottom here is 4 by 9. So we have 2 4 by 9s. So again, this will give us the surface area of the prism. Now we're going to add in a hemisphere. And the hemisphere is a half times 4 pi r squared. So we put the hemisphere on there. That's surface area here. But then the base of our semicircle, this has covered up surface area that we've previously counted. So we're going to have to minus a pi r squared. And we're going to plug in all the r's r2, and then we should be able to solve this. So let's go step by step. 9 by 2 is 18, and we double that, and we get 36. 2 times 4 is 8, and we double that, and we get 16. Plus 4 times 9 is 36. 36 times 2 is 72. So this is just the surface area of the rectangular prism. Now we're going to add in half of 4 is 2, and our radius is 2, so this will be 2 squared. That'll be 4 times 2, or 8 pi. And then we're going to minus here pi r squared. R again is 2, so 2 squared is 4, and times pi is 4 pi. And let's just do this kind of here separate. 8 pi minus 4 pi is 4 pi. So our answer is 36 plus 16 plus 72 plus 4 pi. So that becomes 124 plus 4 pi. And if we punch that in our calculator, we will get approximately 136.6, and our units would be feet squared, squared feet. All right. Letter B is going to be much easier. B is just a cylinder and a full sphere. So we've got half the sphere here. I'll sort of highlight it in red. We've got the other half of the sphere here. I'll highlight in blue. So we're going to have one sphere plus the lateral surface area of our cylinder, our Pringles can there. So let's do the Pringles can first. That lateral area is 2 pi r times the height, or in this case it'll be the length because it's kind of lying on its side. And then we're going to have the surface area of one sphere, 4 pi r squared. All right, 2 is just 2. Pi is just pi. Our radius is given as 8, and our length here is 15. And then we're going to have plus 4 times pi times 8 squared. So 2 times 15 is 30. 30 times 8 is 240. So that's a 240 pi. Plus 8 squared is 64. Times this 4 is 256 pi. And if we add those together, we do get 496 pi inches squared. But I do notice it does say round to the nearest tenth, so I just grab my calculator. 496 times pi key is approximately 1,558.2, and again that would be inches squared as our units. All right, couple more to go. Number 4, 2 pieces of ice have the same volume. The one with the greater surface area will melt faster. One piece of ice shown is a sphere, the other piece is a cube. Given the pieces of ice have approximately the same volume, which will melt faster? And in our picture, we see the cube has side lengths of 24.2 millimeters, and our circular ice spheres have a radius of 15 millimeters. So let's do the sphere. I'll do the sphere here in red ink. Sphere. Surface area of a sphere is 4 pi r squared. 4 pi r squared. Well, we know the r, the radius over here, is 15. So that's going to be 4 times pi times 15 squared. 15 squared is 225. 225 times 4 is 900. So this is 900 pi, and let's get that as a decimal. Approximately 2,827.43 units millimeters squared. All right, now let's do the cube. Cube. The surface area of a cube is 6 times length times width, or base times height. If I draw like a little picture over here. Since it's a cube, each edge is 24.2. 24.2. So each side is going to be 24.2 multiplied by itself. And then we're going to have 6 sides on our cube. So I would just go right to my calculator, 24.2, hit the squared key, multiply that by 6. We got approximately 3,513.84 millimeters squared. And which one will melt faster? The one with the bigger surface area. Here's our biggest surface area. Cube will melt faster. There we go. All right, we got one more practice problem. And this does have a little sort of science tie-in. There are fountains called floating spheres. A person with this giant sphere of stone the water is coming up from below at a pretty good pressure, so that's pushing the sphere up, and then you can easily put your hand on it and turn this giant thousands of pounds of stone with a little bit of effort. It's called a floating sphere. A person can easily spin the granite sphere weighing thousands of pounds. This is due to the force provided by the water in the socket that the sphere rests in. In one such fountain, 5% of the surface of the sphere is in contact with the water. How many square inches is that in contact with the water? Well, we're going to need the full surface area of our sphere, And once again, that formula is 4 pi r squared. It says here the diameter of the sphere is 48, so the radius is half of that, 24. 4 times pi times 24 squared. 24 squared is 576 times 4. That's 2,304 pi, and that would be inches squared. So that's our total surface area, and 5% of that is in contact with the water. So we're going to multiply the 2304 pi by 5%, which as a decimal is 0.05. Slide the decimal 2 to the left. So we punch that in our calculator, and we get 115.2 pi. And if we use our pi key, that's 361.9. And what the heck, let's just round that up to about 362 square inches. Again, that's how much of the surface area of the sphere is in contact with the water jet. Now, the last one's pretty easy. The water in the socket applies a force of 15 pounds per square inch. Well, this is how many inches squared we have. So we're going to multiply our 362 times 15. And my calculator tells me that is about 5,428.7 pounds per inches square. Pounds per inch squared. All right, that's the last slide in my slideshow. That's the last practice problem. Hope the video was helpful, and I will see you in class.